A telescope launched on Christmas Day, and it broke physics. The James Webb Space Telescope pointed into the deep past and found galaxies 100 times too massive, structures 13 million light-years long, and geometric shapes floating in the atmosphere of Saturn that no model on Earth can explain. We are going to visit a chain of dead galaxies that formed before they should have existed. A star wrapped in a sphere of fire, and a six-armed shape with two of its arms missing, drifting silently above the clouds of a distant planet. If you enjoy this, subscribe, because we cover the discoveries that textbooks haven't caught up to yet. Strap in. We begin. Christmas Day 2021, a rocket lifted off from the northeastern coast of South America, carrying the most expensive scientific instrument ever built. The James Webb Space Telescope had been in development for over 20 years. It cost $10 billion. It involved the work of thousands of scientists across 20 countries. And everyone involved had the same expectation going in. The telescope would look deep into the universe, see the earliest galaxies, and confirm the model that astronomers had spent decades building. The Standard Model. The one that explained how everything formed, how long it took, and why the universe looks the way it does today. That is not what happened. Within months of its first observations, the telescope started sending back data that made scientists stop and stare at their screens. The galaxies it found were too big, too old, too massive, too structured. They looked like galaxies that should exist billions of years later in cosmic history, sitting right there at the beginning of time, fully formed and glowing in the dark. Here is the simplest way to picture it. Imagine you are watching a time-lapse video of a city being built. You expect to see empty land, then a few small buildings, then slowly, over decades, a skyline rising. Now imagine that in the very first frame, the city is already finished. Skyscrapers, highways, bridges, all of it. Standing complete before any construction crew ever showed up. That is the problem the telescope revealed, and it only got stranger from there. The James Webb Space Telescope works by collecting infrared light, which is light with a wavelength too long for human eyes to detect. This matters because when the universe expands, it stretches light. Light from very distant objects gets stretched so far that it shifts out of the visible range entirely and into the infrared. The telescope was built specifically to catch that stretched light and pull images out of the deep past, and it pulls them from very deep. The telescope can see objects whose light left them over 13 billion years ago. For context, the universe itself is only about 13.8 billion years old. The telescope is essentially looking at baby pictures of existence. What it found in those baby pictures shattered the timeline. Scientists had a clear prediction. Early galaxies should be small, messy, and still forming. They should look like scattered clouds of gas and young stars slowly clumping together under gravity. The universe at that age simply had not had enough time for anything large and organized to exist. The telescope disagreed. It found massive galaxies, organized galaxies, galaxies that had already lived full lives, galaxies that had already stopped forming stars and gone quiet. All of this in a universe that, by every calculation, should have been far too young to produce any of it. Astronomers started asking uncomfortable questions. Were their calculations wrong? Was the age of the universe wrong? Was the rate at which galaxies grow fundamentally misunderstood? Or was something else happening in the early universe, something invisible and powerful, driving structure to form faster than any known force should allow? Nobody had an answer. And the more data the telescope gathered, the bigger the problem became. The cosmic vine was the discovery that pushed the crisis into full view. A structure so enormous, so organized, and so impossibly early that the moment astronomers saw it, they knew the old model was in serious trouble. What they found in that thin strip of sky between two constellations will change how you picture the universe forever. Deep in a quiet patch of sky, sitting between the constellations Ursa Major and Botes. Astronomers aimed the telescope at a region called the Extended Groth Strip. They were not expecting anything extraordinary. The strip had been studied before. Older telescopes had already mapped parts of it. Scientists were mostly using it as a comparison field, a stretch of sky useful for checking data against known structures. Then, the image came back, and the room went silent. Sweeping across 13 million light-years of space, in the shape of a massive curved bow, was a chain of at least 20 galaxies packed tightly together, all moving in the same direction, all gravitationally linked. Scientists named it the Cosmic Vine. To understand how absurd this is, you need a sense of scale. Our own Milky Way galaxy stretches about 100,000 light-years from one edge to the other. The Cosmic Vine stretches 13 million. That means if you lined up 130 Milky Ways end to end, you would barely match its length. Its total mass sits around 260 billion times the mass of our Sun. And all of this existed when the universe was barely 2 billion years old. Here is why that matters. Gravity is powerful, but it is slow. For a structure of this size to form, gravity needs enormous amounts of time to pull gas clouds together, collapse them into stars, build those stars into galaxies, and then pull those galaxies toward each other across millions of light years. Every step takes billions of years. The Standard Model predicted that structures this large should not exist until the universe was several billion years older than it was when the Vine appears in the data. But there it is, fully formed. Massive, organized, curved like a bow across the dark. The light from the Cosmic Vine took over 11 billion years to reach the telescope's mirrors. That means we are seeing this structure as it existed more than 11 billion years ago. And at that point in time, the universe simply did not have the ingredients, the time, or the gravitational budget to produce something this enormous. Scientists ran the numbers repeatedly. Every calculation returned the same answer. The Cosmic Vine should not exist. The universe was too young, the matter was too spread out, and the forces at work were too slow to have built a chain of this scale in the time available. Some researchers immediately began questioning the formation models. Maybe dark matter, the invisible mass that physicists believe holds galaxies together, works faster than expected under certain conditions. Maybe the early universe had denser pockets of matter that collapsed more quickly. Maybe the model itself is missing a force or a process that no one has measured yet. Every explanation raised more questions than it answered. And then scientists looked more closely at the two largest galaxies sitting at the heart of the Vine. What they found there did not just challenge the timeline, it broke it completely. Inside those two galaxies, something had already ended. Something that, according to every model of how galaxies evolve, should have taken billions of years longer to finish. The Vine had already produced galaxies that were dead. Every galaxy in the universe runs on gas. Gas falls into a galaxy under gravity, collapses into dense clouds, and ignites into new stars. That cycle, gas in, stars born, light flooding outward, is the heartbeat of a living galaxy. Our own Milky Way is still doing it right now. Somewhere in our galaxy, a cloud of hydrogen is collapsing at this very moment, and a new star is beginning to glow. A galaxy that has stopped doing that is called a quenched galaxy. It has run out of the fuel it needs to make new stars, the young blue stars die off first, and all that remains is a population of old, dim, reddish stars slowly fading. The galaxy glows with cold light and goes quiet. To astronomers, it looks like a city after the power has been shut off. Still visible, but no longer alive in the way it once was. Quenching is supposed to be a slow process. Under the Standard Model, it takes billions of years for a galaxy to use up its star-forming gas, shut down its stellar nurseries, and go dark. You would expect to find quenched galaxies in a mature, older universe. The kind of universe that has had time to live and wind down. Inside the cosmic vine, the two largest galaxies are already quenched, and the vine exists at a time when the universe was barely past its toddler years. Those two galaxies somehow burned through their entire fuel supply, built and destroyed generations of massive stars, and fell silent, all before the universe reached its second billion years. That is like a person living a full 80-year life and dying of old age before they turn 10. Scientists have no framework that explains how this happens. One idea being tested is that supermassive black holes at the centers of these galaxies went through a phase of violent, rapid feeding. When a black hole pulls in enormous amounts of gas quickly, it releases jets of energy so intense that they blast the remaining gas out of the galaxy entirely. No gas means no new stars. The galaxy quenches almost overnight in cosmic terms. That process is called quasar feedback. And while scientists have seen versions of it in other galaxies, those examples happen in older, larger, more evolved systems. Finding evidence of it happening this fast, this early, pushes the known limits of the process. Another possibility is that the galaxies experienced an event astronomers call strangulation. Larger structures cut off the supply of fresh gas flowing into a galaxy. Without new material coming in, the existing gas slowly gets used up, and star formation stops. The cosmic vine, as a massive connected structure, might have disrupted the gas flows of its own member galaxies. Both explanations are possible, both are incomplete, and scientists are still trying to figure out which one fits the data or whether something else entirely is responsible. What makes this discovery particularly unsettling is that the quenched galaxies inside the vine are not small. They are two of the most massive members of an already enormous structure. Big, massive galaxies are supposed to live longer, because they hold more gas. These two had more fuel than almost anything else in that era of the universe, and they still burned through it completely. Somewhere out in the early universe, galaxies were growing and dying at a pace that the laws of physics, as we currently write them, cannot account for. And they were doing it with mass that should not even have existed yet. Because when scientists turned the telescope toward 6 separate galaxies from that same early period, what they measured stopped the entire field cold. February 2023. A team of astronomers published a paper that sent shockwaves through the scientific community. They had been studying images from the telescope, looking at a period just 700 million years after the Big Bang. In cosmic terms, that is the universe as an infant, barely out of the dark ages that followed the Big Bang, when matter was still mostly a hot, diffuse fog and the first stars were only just switching on. Inside those early images, they found 6 galaxies, dense, bright, fully structured. And when they measured the mass of those 6 galaxies, the numbers came back wrong. Every single one of them was more massive than any galaxy had any right to be at that age. Some carried up to 100 times more stellar mass than the standard model predicts any galaxy could accumulate in just 700 million years. To picture what 100 times too massive actually feels like, think about it this way. Imagine a newborn baby that weighs as much as a fully grown adult. Its body would need to have grown at a rate that biology makes completely impossible. The food supply, the growth hormones, the time available, none of it would add up. Scientists looking at these 6 galaxies felt exactly that kind of biological shock, except applied to the physics of an entire universe. The standard model is built on a process called hierarchical assembly. Small clumps of dark matter and gas form first. They slowly attract more mass, they merge with other clumps. Over billions of years, those mergers build larger and larger galaxies. The timeline is gradual, like stacking bricks one at a time. These 6 galaxies look like someone skipped every step and dropped a finished skyscraper onto the empty lot. Scientists immediately questioned the data. The telescope had only recently become operational, and early readings are always checked for instrument errors, but the measurements came back consistent across multiple analyses. The galaxies were real, their masses were real, and the physics of how they got that massive that fast had no explanation. One possibility researchers raised was that star formation in the very early universe might have been shockingly efficient. In today's universe, only a small fraction of available gas actually collapses into stars. Most of it gets too hot, gets blasted outward by stellar winds, or stays too diffuse. But maybe in the earliest moments of the universe, conditions were different enough that gas collapsed into stars at a far higher rate, building galaxies at a speed that modern models never accounted for. Another idea is that the Big Bang itself seeded the universe with dense pockets of matter that had no equivalent today. These primordial overdensities would have collapsed much faster than anything the Standard Model predicts, creating massive structures almost immediately after the lights came on. If either of those ideas is correct, the Standard Model needs serious revision. If neither is correct, something even stranger is going on. And here is the part that kept physicists awake at night. These were 6 galaxies in one observation. If 6 exist in that smaller patch of sky, the early universe could be full of them, which would mean that almost everything scientists thought they knew about how the cosmos built itself is off by a factor that cannot be patched with small adjustments. The model that explained all of this was supposed to be airtight. What the telescope revealed was that it had cracks running all the way through it. For decades, cosmologists had a story they trusted. It started 13.8 billion years ago with the Big Bang, an event that filled all of space with a hot, dense mix of energy and matter. As the universe expanded and cooled, hydrogen and helium formed. Gravity pulled that gas into clumps. The clumps collapsed into stars. Stars grouped into galaxies. Galaxies merged and grew over billions of years into the massive structures we see today. This story, called the Lambda Cold Dark Matter Model, made specific and testable predictions. It predicted how big galaxies should be at different ages. It predicted how quickly star formation should ramp up and slow down over cosmic time. It predicted the distribution of galaxy sizes, shapes, and masses across the observable universe. The predictions matched observation after observation for 30 years. Older telescopes confirmed the model again and again. Scientists became confident. Some called it the Standard Model of cosmology. A finished picture. Then the James Webb Space Telescope started filling in the parts of the picture that older telescopes could not reach. The very first problem was timing. The model said that the universe spent its first few 100 million years in near total darkness, a period called the Cosmic Dark Ages, before the first stars ignited and began lighting things up. Then galaxy formation should have started slowly, with tiny, dim objects gradually assembling over the next several billion years. The telescope looked into that expected darkness and found light. Organized, structured, massive light. Galaxies that had no business being there. The second problem was size. The model predicted that early galaxies should top out at a certain mass, because there simply was not enough time for gravity to pull together the material needed to build anything bigger. The 6 galaxies shattered that ceiling. Their mass exceeded the predicted maximum by such a wide margin that researchers started wondering whether the ceiling itself was calculated correctly. The third problem was diversity. The model predicted a fairly uniform progression from small, clumpy early galaxies to larger, smoother later ones. The telescope found mature, disc-shaped galaxies existing right alongside the ancient. Chaotic clumps, the model predicted. Structure and chaos sitting side by side in the same era of the universe, with no clear explanation for why some galaxies evolved so fast while others stayed primitive. Every one of these failures points to the same underlying issue. The model assumes a specific rate of growth driven by cold dark matter and gravity. If the early universe accelerated that growth somehow, whether through a different form of dark matter, a different behavior of gravity at large scales, or some entirely unknown process, then every timeline in the model needs to be rethought. Some physicists began using a phrase that rarely appears in scientific papers: the model is in crisis. Fixing it will take more than new data. It will take new ideas about what the universe is made of and how its most basic forces operate. And just when researchers thought they had catalogued every strange object the telescope was sending back, a new category of thing appeared in the data. Something that looked like a galaxy. Something that looked like a black hole. And something that was, quite possibly, neither. They showed up everywhere. Scattered across image after image from the telescope, tiny reddish specks sat against the black backdrop of deep space. Small, compact, intensely bright in certain wavelengths of light. Scientists called them the little red dots. At first, nobody was alarmed. The early universe contained all kinds of objects, and the telescope was showing researchers things that older instruments had simply missed. The assumption was that the little red dots were ancient galaxies, just smaller and dimmer versions of the massive ones already causing problems. Then, spectral analysis came back and changed everything. Spectroscopy is the process of splitting an object's light into its component colors, the way a prism splits white light into a rainbow. Each element in the universe absorbs and emits light at specific wavelengths, producing a fingerprint that scientists can read. When astronomers ran spectroscopy on the little red dots, the fingerprints did not match galaxies. They matched something else entirely. The light signatures coming from these objects suggested they were sites of extreme energy release, far more concentrated than a typical galaxy. The energy output matched what you would expect from a supermassive black hole pulling in gas at a rate so extreme that the surrounding material heats up to millions of degrees and blasts radiation outward in every direction. But there was a problem with that explanation too. A black hole burning at that intensity should be visible against its surroundings. The little red dots were red and faint in the visible spectrum, hidden behind something. Something that was absorbing the brightest light and letting only certain wavelengths escape. A new theory emerged. Scientists proposed that these objects might be a type of cosmic structure never seen before. A supermassive black hole surrounded by such a dense shell of hydrogen gas that the gas acts like a cocoon, blocking most of the light and letting only the reddest, longest wavelengths pass through. Researchers named the idea the black hole star, or colloquially, a dark star. An object sitting at the boundary between a galaxy and a black hole, massive enough to be mistaken for one, energetic enough to behave like the other, and wrapped in a burning shell of gas that makes it look like neither when viewed from 11 billion light-years away. The little red dots are scattered throughout the early universe in numbers that surprised everyone. If they are all black hole stars, then the early universe produced this exotic type of object on a massive scale. That would mean the very first bright things in the cosmos were not ordinary galaxies at all, but fiery, cocoon-wrapped black holes burning through their surroundings at a furious rate. And if that is true, the history of how the universe lit up for the first time needs to be completely rewritten. Some of the little red dots are confirmed to be unusually compact galaxies. Others match the black hole star description. Some remain unclassified. Scientists are still working through the catalogue, image by image, fingerprint by fingerprint. What they are finding is that the boundary between a galaxy and a black hole is much blurrier than anyone expected. And that blurriness has a direct impact on one of the deepest mysteries in all of physics. Because to understand what these objects are made of, scientists first need to understand what the universe is made of. And the telescope is revealing that even that, the most fundamental question of all, may have the wrong answer. Picture the most violent object in the universe. A supermassive black hole sits at the center of a young galaxy, pulling in gas and dust at an extraordinary rate. As that material spirals inward, it compresses and heats up to temperatures far beyond the surface of any star. It releases more energy in a single second than our sun produces in a million years. And it does this continuously, for millions of years at a stretch. Astronomers are familiar with this kind of object. They call it a quasar, and quasars are found throughout the universe, burning brightest in the era when galaxies were young and gas was plentiful. But the little red dots are not quasars. Quasars are loud. They shine across the entire spectrum of light, from X-rays to radio waves, and they are hard to miss. The little red dots are quiet by comparison. They glow in the infrared, they hide behind their own emissions, and they appear far smaller than any known quasar. The black hole star theory proposes something different from a quasar. In the extreme conditions of the very early universe, a supermassive black hole might have formed inside a dense, collapsing cloud of hydrogen gas so massive that the gas could not escape. Normally, when a black hole eats material, the energy it releases blasts surrounding gas outward. The pressure of that radiation pushes the gas away, limits the black hole's feeding, and eventually starves it. In the black hole star scenario, the cloud is so enormous and so heavy that even the full radiation pressure of an actively feeding supermassive black hole cannot push the gas away. The black hole keeps eating, the gas keeps falling in, and the whole system reaches a bizarre equilibrium where the black hole and its surrounding cloud coexist in a state of permanent, furious consumption. The outer shell of hydrogen gas glows from the intense radiation inside it. It forms a giant sphere surrounding the black hole, heated to extreme temperatures, puffed up by the energy pouring outward from below. That sphere is what we see when we spot a little red dot. We are looking at the outer edge of a burning hydrogen cocoon wrapped around one of the most extreme feeding events in cosmic history. If this theory is correct, these objects could grow to masses billions of times greater than our sun in a fraction of the time it would take a normal galaxy to accumulate that much material. And that would explain something that has been bothering scientists for years. Astronomers regularly find supermassive black holes at the centers of galaxies throughout the universe, including our own. And they have always wondered how those black holes got so big so fast. The standard story of gradual feeding and slow growth does not fully account for the enormous masses observed. The black hole star offers a shortcut, a phase of extreme, uninterrupted growth early in the universe's history that allows a black hole to reach its final mass much faster than any gradual process allows. The data is still being analyzed. But if the little red dots are black hole stars, they represent a phase of cosmic evolution that happened before everything we thought was the beginning. And that forces a question that scientists are only beginning to grapple with. If a black hole can masquerade as a galaxy, and a galaxy can die before it should exist, what exactly is the difference between them? Astronomers always knew that galaxies and black holes were connected. Every large galaxy appears to have a supermassive black hole at its center. Our Milky Way has one, sitting quiet at the moment, called Sagittarius A star. The galaxy Messier 87 has one so massive that scientists photographed it directly in 2019, making headlines around the world. The black hole and the galaxy seem to grow together, influence each other, and evolve together over billions of years. The relationship was assumed to be a partnership. The galaxy forms first from gas and dark matter. The black hole grows at the center over time, fed by material falling inward. They coexist and shape each other through jets, radiation, and gravity. But they remain two distinct things. A galaxy is a structure of billions of stars. A black hole is a point of collapsed matter. separate categories. The little red dots challenge that boundary at its foundation. If the black hole star theory is correct, then some of the objects appearing in the early universe are neither fully a galaxy nor fully a typical black hole system. They are something between the two. A mass of gas so dense that it cannot escape its own black hole, burning from within, glowing from without, carrying billions of solar masses of material in a state that has no clean classification in existing physics. And that matters beyond terminology. Our entire model of how the universe grew assumes that black holes and galaxies follow separate, predictable developmental tracks. Galaxies grow through mergers, black holes grow through feeding. They influence each other at the margins through feedback processes. All of our equations describe these two tracks and how they interact. A black hole star sits off both tracks entirely. It would mean that some of the mass in the early universe was locked into these hybrid objects before galaxies even had a chance to form. That mass was unavailable for the gradual process of galaxy building that the standard model depends on. And if significant amounts of mass were tied up this way, the distribution of matter across the early universe was fundamentally different from what the model assumed. Every galaxy count, every mass estimate, every model of how light spread through the early universe after the Big Bang would need adjustment. The adjustments might be small. They might be enormous. Scientists do not yet know, because they do not know how many little red dots exist across the full observable universe, or how many of them are true black hole stars rather than compact galaxies. What researchers do know is that this blurring of categories has a direct line to the deepest unsolved problem in modern physics. Because the glue that was supposed to hold all of this together, the invisible substance that fills the universe and determines how galaxies form and grow, is now looking shaky. Decades of calculations rested on a specific picture of what dark matter is. That picture is starting to crack. And the crack started long before the telescope launched. The telescope just made it impossible to ignore. You cannot see dark matter. You cannot touch it, detect it with any instrument directly, or produce it in a laboratory. But for decades, physicists have built their entire picture of the universe around it. Dark matter makes up about 27% of everything that exists. Ordinary matter, every star, planet, gas cloud, and human being accounts for only about 5%. The rest is dark matter and dark energy. We know dark matter exists because of what it does to the things around it. Its gravity bends light. It holds galaxies together. Without it, the rotation of galaxies like the Milky Way makes no mathematical sense. The stars at the outer edges spin far too fast to be held in orbit by the visible mass alone. Something invisible is providing the extra gravitational grip. The specific flavor of dark matter that became the foundation of modern cosmology is called cold dark matter. Cold in this context means slow-moving. Cold dark matter particles are heavy and sluggish. They clump together gradually under gravity, forming dense, roughly spherical halos, and galaxies grow inside those halos over billions of years. Cold dark matter predicted a very specific structure for the universe. It predicted that the first objects to form would be small and compact, because gravity needs less time to collapse a small halo than a large one. It predicted that galaxies would grow by merging, slowly building from small to large over enormous timescales. And it predicted that the halos holding galaxies together would be roughly spherical, because that is the natural shape that forms when slow-moving particles collapse under gravity. The telescope looked at hundreds of early galaxies and found something different. Many of the earliest galaxies are elongated. They stretch into long, thin filaments. They look less like compact spheres and more like stretched strands of pasta hanging in the dark. And the cold dark matter model has significant difficulty explaining why that would be. If the halos that seed galaxy formation are spherical, the galaxies that grow inside them should be roughly spherical too. or at least compact. Elongated filaments in the early universe suggest that something was shaping the matter differently. Something that naturally creates long, stretched structures rather than round, dense ones. Cold dark matter also runs into problems at smaller scales. It predicts far more small satellite galaxies around large galaxies than astronomers actually observe. Our own Milky Way should have hundreds of small companion galaxies orbiting it. We find far fewer than the model predicts. This problem has existed for years, and physicists have patched it with various adjustments, but the adjustments never felt fully satisfying. The new data from the telescope piles additional pressure on a model already showing its age, and here is where something unexpected entered the conversation. A group of physicists began asking whether the problem with dark matter was not its amount, but its nature. What if dark matter was cold in the wrong way? What if the particles making up dark matter were so light, so quantum, so strange, that they did not behave like particles at all? What if dark matter was fuzzy? Every particle in the universe has a dual nature. At the scale of atoms and electrons, quantum mechanics rules, and quantum mechanics says that particles do not have a single definite position. Instead, they exist as waves of probability, smeared out across space until something forces them to settle into a location. An electron is not a tiny dot sitting in one place. It is a blur of possibility, a wave function that collapses only when measured. For everyday objects, this quantum fuzziness is completely invisible. A baseball or a car is made of so many particles that their individual quantum behaviors average out into something solid and predictable. Quantum effects matter at the tiny scale. At the scale of galaxies, they disappear, unless the particles are extraordinarily light. In quantum mechanics, the lighter a particle is, the longer its wavelength. The longer the wavelength, the more spread out and wave-like it behaves. A particle heavy enough to be called cold dark matter has a wavelength so tiny it is completely negligible, and it behaves like a classical, predictable object that clumps under gravity in spherical halos. But physicists began exploring an idea. What if dark matter was made of particles so impossibly light that their quantum wavelength was enormous, millions of light years enormous? What if a single dark matter particle, in the quantum sense, was smeared out across a region of space as large as a galaxy? These particles have a name, ultralight axions, and the model built around them is called fuzzy dark matter. If dark matter is fuzzy, the universe does not behave like a collection of slow-moving cannonballs falling together under gravity. It behaves like an ocean, a vast quantum ocean, with dark matter rippling and interfering with itself across cosmic scales. The waves would wash across millions of light years, and the peaks of those waves would be where matter clumps together and galaxies begin to form. The critical difference is what shapes those clumps. Wave interference does not produce spheres. It produces filaments, sheets, and tangled webs, because that is what happens when waves overlap and reinforce each other. Standing waves create long, stretched ridges of high density, not compact balls, and that is exactly what the telescope sees in the early universe. Long, stretched filaments of galaxies. Tangled, cosmic webs. Structures that look far more like wave interference patterns than the product of slow, spherical halos collapsing under cold, dark matter. The cosmic vine itself, that 13 million light-year bow of galaxies, has exactly the shape you would predict if dark matter were fuzzy. A long, curved, massive filament, shaped by wave dynamics rather than classical gravity. Scientists have not confirmed fuzzy dark matter. It remains a model, not an established fact. The particles it proposes have never been detected directly. Experiments searching for ultralight axions are underway, but finding a particle with a wavelength measured in millions of light years requires instrumentation that does not yet exist. But the shapes the telescope keeps revealing make the fuzzy dark matter case harder to ignore with every new image. And those shapes have a consequence that reaches far beyond the question of what dark matter is. Because if dark matter creates waves, then the structure of the entire universe, on the largest scales imaginable, is a product of quantum mechanics, and that opens a door to something even bigger and stranger. Stand in the ocean up to your waist. Watch two waves from different directions meet at your position. Where they overlap, the water rises higher than either wave alone. Where the peaks of one wave meet the troughs of another, they cancel out and the water goes flat. This is called interference, and it is one of the defining behaviors of waves. Now scale that up by a factor of roughly 100 quadrillion. Instead of water, the medium is dark matter. Instead of wavelengths measured in feet, the wavelengths are measured in millions of light years. And instead of the effect lasting seconds, the interference pattern holds for billions of years, slowly shifting and evolving as the universe expands. In that picture, the peaks of the interference pattern, the places where fuzzy dark matter waves reinforce each other and build up density, are exactly where galaxies form. Not in spherical blobs, because waves do not produce spheres. Waves produce ridges, sheets, filaments, long, sinuous strands of high density with vast empty spaces between them, because that is what interference looks like at any scale. Astronomers already know the universe has large-scale structure. When you map out the positions of millions of galaxies, they do not scatter randomly. They arrange themselves into a vast cosmic web, with galaxies and galaxy clusters sitting along filaments, sheets, and at the nodes where filaments intersect, while enormous empty voids stretch between them. This cosmic web was already known and was mostly explained by the standard cold dark matter model. But the cosmic web predicted by cold dark matter and the one revealed by the telescope are beginning to look different in the details. Cold dark matter predicts more small, isolated clumps. The telescope finds more elongated, connected structures, particularly in the early universe. The filaments appear sooner, stretch longer, and hold more mass than the cold dark matter model comfortably allows. Fuzzy dark matter reproduces those features naturally. Because quantum waves at cosmic scale would suppress the formation of small, compact objects, the same way ocean waves do not create tiny neat spheres of water, but instead build long, rolling ridges. The early universe under fuzzy dark matter would look exactly like what the telescope sees. Fewer small clumps, more stretched filaments, larger organized structures appearing earlier. There is also a specific prediction fuzzy dark matter makes about the cores of galaxies. Cold dark matter predicts that galaxy centers should be extremely dense, with dark matter packing tightly toward the middle. Fuzzy dark matter predicts that the quantum nature of the particles would resist that packing. The center of a galaxy should have a flat density core, a smooth plateau, rather than a sharp spike. Observations of small dwarf galaxies have long hinted at flat cores rather than sharp spikes. This has been one of the persistent, uncomfortable facts for the cold dark matter model. Under fuzzy dark matter, flat cores are a natural result. Every one of these clues points in the same direction, and they are all pointing toward the same uncomfortable conclusion, that the universe, on its largest scales, is quantum mechanical, that the shapes of galaxies, the distribution of matter across billions of light years, and the structure of the cosmic web are all products of quantum wave behavior operating at a size that human intuition simply cannot picture. And if that is true, then the expansion of space itself, the measurement that sits at the heart of all of cosmology, might also be misbehaving. Because two of the most precise instruments in history have now measured how fast the universe is growing, and they are getting completely different answers. Edwin Hubble discovered in the 1920s that the universe is expanding. Every galaxy is moving away from every other galaxy, and the farther away a galaxy is, the faster it appears to recede. This relationship between distance and recession speed is captured in a number called the Hubble constant. It tells you how quickly a patch of space 1 megaparsec wide, roughly 3 million light years, grows with time. For decades, pinning down the exact value of this constant was one of the central goals of observational astronomy. Scientists spent enormous effort building more precise instruments and making more careful measurements. The Hubble Space Telescope, launched in 1990, was named partly in honor of this effort. One of its main jobs was to nail down the Hubble constant with enough accuracy to close the debate. It did. Sort of. Two independent methods of measuring the expansion rate both produced precise answers. But the answers were not the same. The first method measures the expansion by looking at the cosmic microwave background, the faint afterglow of radiation left over from the Big Bang itself. By analyzing the tiny temperature fluctuations across this ancient light, scientists can calculate what the expansion rate should be if the standard model is correct. This method gives a specific number. The second method measures the expansion by looking at standard candles, objects with known brightness. Type 1 supernovae are a favorite tool here. Because physicists know how bright these stellar explosions are in absolute terms, measuring how bright they appear from Earth tells you exactly how far away they are. Combined with how fast they appear to be receding, that gives you the expansion rate. This method gives a different number. The gap between the two measurements is called the Hubble tension, and the James Webb Space Telescope was supposed to resolve it. More precise instruments, more careful calibration, and the debate would close. Instead, the telescope confirmed the gap. Both measurements became more precise, and they remained stubbornly, consistently different. That matters enormously. The Hubble constant is one of the most fundamental numbers in all of physics. Every cosmological model, every prediction about the fate of the universe, every calculation about how structures grow and spread is built on it. If two careful, independent methods of measuring it consistently disagree, then at least one of them is capturing something the standard model does not account for. Some physicists propose that dark energy, the force driving the expansion, is not constant. Maybe it changes over time. Maybe it clumps in certain regions the way matter does. If dark energy behaves differently in different parts of the universe, the two measurement methods would naturally produce different results, because they are sampling different regions at different times in cosmic history. Others propose that the measurements themselves are revealing the truth, that the universe expands unevenly. Some regions of space pull apart faster, others move more slowly. The universe is not a smoothly inflating balloon, it is something lumpier, something that standard equations were never designed to handle. That unevenness has a name, and what it means for our picture of the cosmos is darker and stranger than most people outside physics have yet realized. The entire standard model of cosmology rests on a single assumption. The universe is homogeneous and isotropic. Those are technical words for two simple ideas. Homogeneous means the universe looks basically the same in every location. No special patches that are fundamentally different from the rest. Isotropic means it looks basically the same in every direction. No preferred axis, no special orientation. Together, these two ideas form what physicists call the cosmological principle. And it is not just a background assumption buried in a footnote, it is the load-bearing foundation of every equation in modern cosmology. Remove it, and the entire mathematical structure of the standard model collapses. The cosmological principle was a reasonable assumption for a long time, and observations seem to support it. At the very largest scales, hundreds of millions of light years and beyond, the universe does look roughly uniform. Clusters of galaxies and voids are sprinkled throughout in a pattern that, when you zoom out far enough, appears fairly smooth. But the Hubble tension is evidence that the principle may be cracking. If the universe expands at different rates in different directions, or in different regions, then it is not truly isotropic or homogeneous. There are preferred regions, places where dark energy is stronger, or where matter is denser, or where some unknown force is acting differently than it does elsewhere. And that preference violates the cosmological principle directly. The implications are cascading. Every distance measurement in astronomy relies on assuming uniform expansion. If expansion is uneven, then the distances we have calculated for billions of galaxies are slightly wrong. And if those distances are wrong, then the masses we calculated from those distances are wrong. And if the masses are wrong, then our entire map of how matter is distributed across the observable universe is wrong. A wrong map means wrong models. Wrong models mean wrong predictions. And wrong predictions mean that the picture of the universe we have been building for a century might be systematically off in ways that small corrections cannot fix. This is not a minor technical concern. Physicists use the standard cosmological model to predict how the universe will evolve billions of years into the future. They use it to understand the fate of stars, galaxies, and eventually Earth itself. If the model rests on a cracked foundation, those predictions carry cracks too. Some researchers argue that the cosmological principle is still valid at the very largest scales, and the tension is just a measurement artifact or a gap in understanding dark energy. Others argue that the telescope data is forcing the field to consider that the universe has structure on scales even larger than the cosmic web, structure that creates genuine regional variations in expansion. And then there is the strangest possibility of all. That dark energy is alive in some sense, changing and clumping the way matter does, creating a universe that is genuinely lumpy at its largest scale rather than smooth. Every version of this problem leads to the same place, a rewriting of the equations at the foundation of physics. And while scientists debate what is happening at the edge of the observable universe, the telescope kept turning up impossible things in unexpected places, some of them in the most familiar part of space, some of them in a direction that none of the theorists predicted. Imagine standing on a rubber sheet stretched in all directions at once. If the sheet stretches uniformly, every point moves away from every other point at the same rate. 2 points 10 inches apart move apart at the same relative speed as 2 points 1 inch apart. The whole thing scales smoothly, and no location has any special relationship to any other. Now imagine the sheet stretching faster in one corner than another. Some patches pull outward quickly, others barely move. Suddenly, the uniform grid drawn on the sheet warps into something uneven. Points that started equal distances apart end up at wildly different separations depending on which corner they happen to be near. The sheet develops lumps. This is what clumping expansion looks like in space. And the James Webb Space Telescope confirmed that it is happening. When astronomers use the telescope to measure galaxy distances and recession speeds across different regions of the sky, the numbers do not come out uniform. Some patches of the observable universe appear to be pulling apart slightly faster than others. The difference is small enough that older instruments missed it, but precise enough that the telescope can measure it clearly. One concrete consequence of clumping expansion is something called a bulk flow. Galaxies in a particular region all appear to drift in a shared direction, as if they are all being dragged by the same underlying current. Scientists have measured bulk flows before, but the James Webb Space Telescope is now revealing them at scales and speeds that exceed what the standard model predicts. A particularly striking case is a structure some astronomers call the Dipole Repeller. It is a massive underdense region of space that appears to be pushing galaxies away from it, while a dense region called the Great Attractor on the opposite side pulls them inward. Our own Milky Way is caught between these two forces, drifting through space in a direction partially shaped by this imbalance. That drift was already known, but the new data suggests the imbalance is stronger and more structured than previously measured. The clumping also affects how we interpret the little red dots, the cosmic vine, and the oversized early galaxies. All of those discoveries were made using distance measurements that assumed uniform expansion. If expansion is actually clumped, then some of those objects might be slightly closer or farther than currently calculated. Their masses and sizes might need adjustment. The adjustments could be small, or they could be significant enough to resolve some of the conflicts with the standard model, shifting some of the impossibly massive early galaxies into a range that the model can almost accommodate. But even if adjustments shrink the problem, they do not eliminate it. The clumping itself is still unexplained. The model predicts a smoother universe than the telescope reveals. Something is driving the unevenness. Something is making space expand faster in certain regions, and no one has a satisfying explanation for what that something is. Dark energy remains the leading candidate, but dark energy, as currently defined, is a uniform background pressure pushing everything outward at the same rate everywhere. A dark energy that clumps and varies by region is a different beast entirely. Physics may need a new name for it, and understanding it will require going back to where the James Webb Space Telescope found its most stunning and most impossible structure. Back to that quiet strip of sky and a chain of galaxies that should not exist. In the 1990s, astronomer Edward Groth led a survey using the Hubble Space Telescope. The target was a narrow, elongated region of sky located between the constellations Ursa Major, the Great Bear, and Botes, the Herdsman. At first glance, there was nothing special about it. The strip did not contain any famous nebulae, nearby stars, or previously known structures. It was chosen partly because it was far from the plane of the Milky Way, meaning the view outward was unobstructed by dust and gas from our own galaxy. The original survey captured thousands of galaxies in the strip, a deep slice of the universe at various distances. Astronomers used it as a calibration field, a reference point for comparing data from other observations. For years, the extended Groth strip was a useful but unremarkable patch of sky. Then the James Webb Space Telescope looked at it. The telescope did not scan the strip casually. It made deep, precise, multi-wavelength observations designed to capture the faintest possible objects at the greatest possible distances. And in those images, buried among the thousands of known galaxies and smudges of light, the cosmic vine appeared. At first, it looked like a coincidence, a few galaxies scattered in a rough line, but when researchers mapped their distances using spectroscopy, measuring the redshift of each object to determine how far away it was, something remarkable became clear. These galaxies were not just visually close together from Earth's point of view, they were actually close to each other in three-dimensional space. They existed at essentially the same distance from Earth, meaning the same distance in cosmic time, all clustered along a single massive structure. 20 confirmed massive galaxies, possibly more smaller ones still being catalogued. All arranged in a curved bow shape, stretching across 13 million light-years, all living in the same narrow window of cosmic time, their light travelling for over 11 billion years before reaching the telescope's gold-plated mirrors. The discovery happened partly because of technology, and partly because of patience. The telescope stared at the strip for long periods, collecting enough light from each object to run spectroscopic analysis. Without that depth of observation, the vine would have remained invisible, just a scattering of red smudges with no obvious connection to each other. The extended Groth strip is also a reminder of a fundamental truth about cosmological discovery. The universe does not reveal itself evenly. It hides its strangest structures in patches of sky that look ordinary until you look long enough. Every deep field survey in astronomy's history has produced surprises that rewrote textbooks. The Hubble Deep Field in the 1990s revealed that the universe contained 10 times more galaxies than anyone expected. The James Webb Deep Fields are doing the same, at higher resolution, greater depth, and with discoveries that cut to the foundation of physics rather than just revising galaxy counts. And the cosmic vine is doing something physical, something measurable, to the space around it. Something that lets astronomers glimpse structures even farther behind it, hidden until the vine itself bends the light and reveals them. Light travels in a straight line. That is one of the most basic rules in physics. Light does not curve, does not bend, does not take detours. It moves in a perfectly straight path from its source to wherever it lands. Unless it passes near something with enormous mass, because mass bends space itself, and when space bends, the straight path that light follows curves with it. Albert Einstein predicted this in 1915. A few years later, an observation during a solar eclipse confirmed it. Starlight passing close to the sun arrived at a slightly different position than expected, because the sun's gravity had warped the space around it and bent the path of the light. The confirmation made Einstein world famous almost overnight. The effect is called gravitational lensing. And with enough mass, it can do something extraordinary. A massive object sitting between Earth and a more distant source of light can act like a magnifying glass, bending the light from the distant source around itself and focusing it toward us. Sometimes the result is a smeared arc of distorted light. Sometimes it produces multiple images of the same object, appearing in different positions around the lens. Sometimes, when the alignment is nearly perfect, it creates a full ring of light, called an Einstein ring, encircling the massive object. The cosmic vine is massive enough to act as a gravitational lens. Its total mass, estimated at 260 billion times the mass of our Sun, creates a significant curvature in the space around it. Light from galaxies and structures sitting far behind the vine, objects that would otherwise be too faint and too distant to detect, gets bent around the vine and magnified toward the telescope. This turns the vine into a tool. Astronomers studying it are not just learning about the vine itself, they are using it as a natural telescope extension, accessing light from objects even further back in time than the vine, objects sitting in an era of the universe so early that even the James Webb Space Telescope would struggle to see them without the lensing boost. Every gravitational lens discovery adds to a growing catalogue of structures, arcs, rings, and distorted images spread across the deep field images. Scientists cross-reference these distortions against known lens positions to reconstruct the three-dimensional distribution of mass in the field, producing maps of where matter is concentrated, including dark matter, which produces lensing effects just like ordinary matter. The lensing data from the extended Groth strip is already revealing that the cosmic vine is surrounded by a much broader filament of matter than the visible galaxies suggest. The dark matter halo extending from the structure is enormous, stretching far beyond the visible edges of the vine itself. The structure is even more massive than the galaxy count alone implied. And the more massive it is, the sharper the question becomes. How did it get that heavy, that fast? The standard model cannot assemble this much mass into a single connected structure in the time available. Something accelerated the process, and that acceleration points back to a problem that has been lurking in every chapter of this story. The timeline. The way the universe actually grew is wildly different from the way every model predicted it would. And to see exactly how different, you have to look at what the standard model promised would be there and compare it, point by point, with what the telescope actually found. Everything in cosmology runs on time. Every structure in the universe, every star, every galaxy, every cluster of galaxies is the product of a process that takes a specific amount of time to complete. Gravity pulls matter together at a rate that physicists can calculate precisely. Gas clouds cool and collapse at rates governed by thermodynamics. Stars ignite, burn, and explode on schedules set by nuclear physics. The universe's entire history is a clock, and every structure is a tick on that clock. The standard model does not just describe these processes, it predicts them. Given the conditions right after the Big Bang and the known behavior of matter and gravity, the model tells scientists what should exist at every point in cosmic history. Small, chaotic objects in the first billion years. medium-sized galaxies forming and merging over the next few billion, large galaxy clusters appearing only well into the universe's second half of its current age. The cosmic vine appears at a point on that clock when large, organized, connected structures should be completely impossible. Here is the timing. The universe is 13.8 billion years old today. The light from the cosmic vine has a redshift of 3.44, which means it traveled for over 11 billion years to reach the telescope. We are seeing the vine as it existed when the universe was roughly 2 billion years old. That is about 14% of the universe's current age. In those 2 billion years, gravity had to take the near-uniform distribution of matter after the Big Bang and somehow assemble at least 20 massive galaxies, lock them into a gravitational structure stretching 13 million light-years, and reach a total mass of 260 billion solar masses. Physicists ran the simulations. Under the standard cold dark matter model, the largest structures that should exist at that age are much smaller, much more loosely connected, and carrying far less total mass. The vine exceeds every predicted limit by a significant margin. The problem is not that the structure is large. The problem is the rate at which it grew. Every doubling of mass takes time. The more mass you are trying to accumulate, the more time you need, because there is a ceiling on how fast gravity can pull material in, and how quickly that material can dissipate the energy of collapse and settle into a stable structure. The universe's expansion also fights against gravity, stretching space outward and making it harder for distant clumps of matter to fall toward each other. The vine somehow beat all of these limits. One proposed solution is that the region of the universe containing the vine had an unusually high concentration of matter right after the Big Bang, a primordial overdensity, a patch slightly denser than average from the very beginning, would have collapsed faster and earlier than surrounding regions. Combined with a faster than expected rate of star formation, an overdense seed could potentially produce a massive structure earlier than standard predictions allow. But the simulations of even that optimistic scenario fall short of producing something as large as the vine at 2 billion years. The overdensity would need to be so extreme that it strains the predictions of inflation, the period of rapid expansion just after the Big Bang that is supposed to have smoothed out most of these density variations. Every solution to the vine's timeline problem creates new problems elsewhere in the model. Scientists are not finding a missing piece, they are finding a gap in the foundation. And the strangest part of this entire story is that the impossible structures the telescope found are not limited to the deep past of the early universe. Some of them are right here, inside our own solar system, floating in the atmosphere of a planet we have been watching since the invention of the telescope. What the James Webb Space Telescope found above Saturn is something no model of planetary science predicted, and something no one on Earth can currently explain. About 5,000 light-years from Earth, in the constellation Cygnus, two stars are locked in a slow, grinding orbit around each other. One of them is ordinary enough, a massive O-type star, hot and blue, pumping out intense radiation. The other is one of the rarest and most violent types of star known to science, a Wolf-Rayet star. These are the dying giants of the stellar world, stars so massive that they burn through their fuel at a catastrophic rate, blasting their outer layers into space in a ferocious wind of gas and particles. Most Wolf-Rayet stars live fast and die in spectacular supernova explosions. This one, called ROR-140, is doing something stranger before it dies. Every 8 years, the two stars in the system reach their closest point to each other. When they do, their stellar winds collide. The O-type star blows its wind outward. The Wolf-Rayet star blows its own powerful wind in the opposite direction. Where the two winds meet, the pressure and temperature spike. Carbon atoms in the Wolf-Rayet wind crystallize out of the gas, forming grains of dust. That part is not unusual. Dust formation in binary star systems is known and understood. The shape of what forms next is not understood at all. In August 2022, the telescope captured an image of R140 that stopped astronomers cold. Surrounding the star system was a series of concentric shells of dust, each one a near-perfect geometric ring expanding outward from the stars. The rings were evenly spaced, they were sharply defined, and they were square, not circular. Square, each ring had 4 sides, 4 corners, and a regularity that looked almost designed. The shells sat nested inside each other like a series of squared-off ripples moving outward from a stone dropped in a still pond. Except the stone was a dying star system and the pond was deep space. Scientists had no immediate explanation. Dust shells from binary stars are expected to be roughly spherical, expanding outward in all directions at roughly equal rates. A sphere viewed from Earth looks like a circle. There is no known physical process in stellar astrophysics that should produce a 4-sided geometric shape from a stellar wind. Stellar winds are not aware of geometry. They do not have corners. One early hypothesis involved the orientation of the 2 stars' orbital plane and the way their winds intersect. If the collision zone between the 2 stellar winds is shaped in a particular way, the dust that forms might get channeled into a specific geometry rather than spreading uniformly. The mathematics of that scenario are complicated, and researchers spent months working through whether the orbital mechanics could produce the observed shape. The numbers came close, but did not fully match. The rings are more regular than any model produced. The corners are sharper than the orbital mechanics should allow, and the shells are more evenly spaced than any collision zone model predicts. Another possibility involves the nature of the dust itself. Carbon dust grains interact with radiation pressure, the outward push of light from the star. If the radiation from both stars creates a pressure field with a specific geometry, the dust might align itself to that field and crystallize in a pattern shaped by the radiation rather than by simple outward expansion. That idea is still being modeled. What scientists agree on is simpler and more unsettling. An object 5,000 light-years away is producing perfect geometric shapes in space. Every 8 years, a new ring forms. The rings are expanding outward at a measurable speed, and physics, as currently written, cannot fully explain why they are square. The universe, it turns out, has a habit of producing precise shapes where none should exist, and nowhere is that more true than in the place scientists least expected to find them. The squares around BR140 are not a one-time anomaly. They are a pattern. Each 8-year orbit of the binary system produces another ring of dust, expelled at the close approach of the 2 stars, then carried outward by the expanding stellar winds. By the time the telescope imaged the system, at least 17 distinct rings were visible, nested concentrically in the infrared light that the telescope captures. 17 passes. 17 rings, each one an almost perfect square expanding outward at a rate of about 2.5 million miles per hour. To understand why this is so strange, you need to understand how stars normally shed material. When a star loses mass through its outer layers, whether through a gentle stellar wind or a more violent eruption, that material expands outward in every direction equally. The expansion is isotropic, meaning it has no preferred direction. The result is a sphere. A spherical shell of gas expanding outward at the same speed in every direction, like an inflating balloon. When astronomers observe planetary nebulae, the glowing shells of gas left behind when stars like our sun die, they see spheres. Sometimes the spheres are distorted by magnetic fields or companion stars into elongated shapes, butterflies, hourglasses, and rings. But the basic geometry is always curved. Nature does not produce flat sides and sharp corners in expanding gas. WR140 produces flat sides and sharp corners. 17 times in a row. This consistency is the most troubling part. An anomaly can be noise, a measurement error, a one-time quirk of conditions, but a repeating pattern with 17 occurrences is data. Something physical is imposing this shape on the expanding dust, and it does so with enough regularity to produce rings that are nearly identical to each other, just at different sizes. The most promising physical explanation currently being modelled involves the interaction between the two stellar winds and the orientation of the star's orbit. When the two stars reach their closest point, called periastron, the collision zone between their winds forms a specific three-dimensional shape determined by the speed and density of each wind, the angle of the orbit, and the relative positions of both stars. Researchers propose that this collision zone acts like a nozzle, channeling the freshly formed carbon dust grains into a sheet rather than a sphere. As the binary system orbits, that sheet wraps around the stars in a shape influenced by the orbital plane. The mathematics suggest that, under certain orbital conditions, the wrapping could produce a squared-off geometry when viewed from certain angles, but this model depends heavily on viewing angle. From a different position in space, the rings might not look square at all. They might appear as skewed ellipses or irregular blobs. The fact that they appear so symmetrically square from Earth's vantage point could be partly a projection effect. Scientists are still testing this. If future observations show that the square shape holds across multiple observing angles, or if other instruments detect asymmetric emission that reveals the true three-dimensional structure of the rings, the projection hypothesis will either strengthen or collapse. What makes RR 140 compelling beyond its own strangeness is what it represents. A star system producing geometry where no geometry should exist is interesting. Multiple stars doing similar things, structures appearing where physics says they should not, is a pattern. And the universe, as the James Webb Space Telescope keeps revealing, is full of patterns that physics cannot yet explain. One of those patterns sits in a place far closer to home than any of the other anomalies. Inside our own solar system, orbiting the same sun that lights up our sky every morning, a planet is wearing geometric shapes in its atmosphere that no scientist predicted, and no model can fully account for. Saturn is one of the most studied planets in the solar system. Decades of spacecraft visits, including the Cassini mission that orbited Saturn for 13 years, produced enormous amounts of data on its atmosphere. Rings, magnetic field, and moons. Scientists believed they had a solid understanding of how Saturn's atmosphere works, what gases fill each layer, how those gases move, and what forces drive the planet's banded appearance. Then, in September 2025, the James Webb Space Telescope turned its infrared instruments toward Saturn. What it found in the northern hemisphere shook planetary scientists. Between 55 and 65 degrees north latitude, running in a band encircling the planet, was a chain of dark structures. In the infrared images, they appeared as discrete, separate blobs spaced along the band like beads on a string. Each one absorbed infrared light rather than emitting it, making them appear as dark patches against the brighter background of Saturn's atmosphere. The structures sit about 683 miles above Saturn's visible cloud tops, placing them in a region of the atmosphere called the ionosphere. The ionosphere is the uppermost layer of a planetary atmosphere, where solar radiation strips electrons from gas molecules and creates a zone of charged particles. Scientists had never seen structures like this before. The dark beads had no equivalent in any other planetary atmosphere in the solar system. Their infrared absorption signature suggested they were not simple clouds of gas or ice crystals. They were absorbing specific wavelengths in ways that hinted at a different kind of material. Possibly complex organic molecules, possibly carbon compounds, possibly something else entirely. The beads were also moving. Tracking them across multiple observations, scientists confirmed they were drifting slowly within their latitude band, carried by high-altitude atmospheric winds. But their internal structure remained stable over the observation period, meaning they were not random turbulent eddies that form and dissolve quickly. They persisted. They held their shape. That stability is one of the most puzzling aspects. In atmospheric science, stable structures at high altitudes require specific conditions to maintain themselves against the mixing and turbulence that characterize planetary atmospheres. The mechanisms that could create and maintain stable, discrete structures in Saturn's ionosphere are not well understood, and the specific conditions at the altitude where the beads sit make them even harder to explain using known atmospheric physics. Saturn's ionosphere is primarily driven by its interaction with the magnetic field and by solar radiation. Both of those forces act more or less uniformly across the planet at a given latitude, which should produce uniform atmospheric layers rather than discrete, separated blobs. The fact that the beads are localized, separated by gaps, and arranged in a chain rather than blending into a continuous band suggests that some additional organizing force is acting on the material. What that force is, physicists do not know. The discovery immediately raised another question. Were the dark beads connected to Saturn's famous auroras, the glowing curtains of light that appear near its poles when charged particles from the sun interact with its magnetic field? Or were they connected to some other known atmospheric process? Scientists checked both possibilities. The answer to both was the same. And that answer made everything stranger. The first thing researchers did after confirming the dark beads were real was look for a known cause. Saturn's magnetic field is powerful. It generates vast magnetospheric currents that interact with the planet's atmosphere, particularly at the poles, producing auroras visible to telescopes and spacecraft alike. Those auroras create heating effects that can alter the chemistry of the upper atmosphere. Scientists have found that Saturn's auroras pump energy into the ionosphere, creating detectable changes in the density and composition of the gas layers nearby. Could the dark beads be connected to this process? The team checked the latitude. Saturn's auroral activity is centered at high latitudes, close to the poles. The dark beads sit between 55 and 65 degrees north. That is outside the typical auroral zone. The correlation was weak at best. They checked whether the bead positions tracked with known magnetic field structures. Saturn's magnetic field has specific zones of activity, where field lines converge and where energetic particles preferentially rain down into the atmosphere. If the beads were driven by magnetic particle precipitation, they should cluster near those zones. They did not. The beads showed no consistent alignment with Saturn's known magnetic structures. They checked for connections to Saturn's ring system. Saturn's rings are not just decorative. They interact dynamically with the planet's ionosphere through a process called ring rain, where charged particles from the rings spiral down magnetic field lines and deposit material into specific latitude bands of the upper atmosphere. This process creates detectable enhancements in certain atmospheric components and even affects the brightness of Saturn's infrared emission in some regions. The dark bead latitude band does not match any known ring rain deposition zone. Researchers also ruled out instrument error. The James Webb Space Telescope uses highly sensitive near-infrared and mid-infrared detectors, and its data is cross-calibrated extensively before publication. The beads appeared consistently across multiple observation filters and across multiple observation sessions. They are real atmospheric structures, confirmed by the data. After eliminating every known atmospheric driver, the scientific team was left with an honest and uncomfortable conclusion. The dark beads are driven by an unknown mechanism. That phrase, unknown mechanism, appears rarely in planetary science papers. Scientists almost always have at least a plausible candidate process, even if it is unconfirmed. The fact that the team found no plausible candidate means the beads represent a genuinely new phenomenon, something outside the current vocabulary of atmospheric physics. What makes this even more striking is the location. Saturn is one of the best studied planets in existence. It has had a spacecraft orbiting it for over a decade. It has been observed by ground-based telescopes for centuries, and yet it hid these structures from every instrument until the James Webb Space Telescope looked in the right wavelength at the right time. The infrared sensitivity of the telescope was the key. Human eyes and most earlier telescopes see primarily in visible light. The dark beads absorb infrared, not visible light. To a visible light telescope, they would be invisible. This means these structures may have been present for an unknown length of time, sitting in Saturn's atmosphere undiscovered, simply because no sufficiently sensitive infrared instrument had looked for them before. And directly below them, in a layer of the atmosphere sitting 400 kilometers lower, was something even more geometrically precise, something that no model of any planet anywhere could have predicted. 400 kilometers below the dark beads, in Saturn's stratosphere, the telescope found something that made the beads look ordinary. A massive geometric shape. 6 arms radiating outward from a central point, 2 of the arms missing, leaving an asymmetric figure that sat dark and still against the surrounding brightness of the planet's upper atmosphere. Scientists stared at the images. They ran the data through calibration checks. They compared it against known atmospheric features on every planet in the solar system. Nothing matched. The stratosphere is a layer of the atmosphere where temperature increases with altitude rather than decreasing, because ozone and other compounds absorb ultraviolet radiation and release that energy as heat. On Earth, the stratosphere sits between roughly 7 and 30 miles up and is home to jet streams, atmospheric waves, and the ozone layer. On Saturn, the stratosphere occupies a comparable region and is known to contain complex hydrocarbon chemistry, driven by the breakdown of methane by sunlight. A 6-armed geometric shape floating stably in that layer has no explanation in any of this chemistry. Hydrocarbons do not spontaneously arrange themselves into star shapes. Atmospheric waves do not produce sharp, radiating arms. Temperature gradients and pressure systems create bands, eddies, and vortices, not stars. The shape has 4 confirmed arms and 2 gaps where the remaining arms should be, creating a figure that is roughly star-like, but incomplete. The asymmetry is itself strange. The 4 visible arms are not perfectly evenly spaced, but they are regular enough to clearly suggest a 6-fold symmetry in the underlying process, with 2 arms either absent from the start or dark enough to be invisible in the current data. Saturn's North Pole is already famous for one geometric atmospheric feature, a massive 6-sided hexagonal storm about 18,000 miles wide. Sits at the pole and has been observed since the Voyager spacecraft flew past in the 1980s. Scientists spent years working out an explanation for the hexagon, eventually concluding that it is produced by a phenomenon called a standing Rossby wave, a type of atmospheric wave that becomes locked into place by the specific rotation rate of the planet and the interaction of its winds at a particular latitude. That explanation works for the polar hexagon. It does not transfer easily to the stratospheric star shape. The star sits at a different altitude, a different latitude, involves a different geometry, and behaves differently from the polar hexagon. The Rossby wave mechanism produces patterns tied closely to the planet's rotation rate and the behavior of jet streams, factors that are very specific to latitude and altitude. The stratospheric star appears in a region where those specific conditions do not apply in the same way. Some researchers have proposed that the star shape could be a kind of standing wave pattern, created by interference between multiple atmospheric waves moving in different directions. When multiple wave systems overlap, their interaction can create nodes of constructive interference, where the waves reinforce each other and produce high contrast structures. If 4 waves from different directions intersected in a way that created a 4-armed pattern, and a slight asymmetry or phase difference suppressed 2 of the expected 6 arms, the result might look like what the telescope captured. That idea is speculative. No atmospheric simulation has yet reproduced the shape, and between the stratospheric star and the dark beads above it lies a region of Saturn's atmosphere that no instrument has ever fully measured. A gap 400 kilometers deep, filled with unknown chemistry and unstudied dynamics, sitting between two of the strangest atmospheric features ever discovered. Saturn's atmosphere has layers. Like a cake with distinct tiers, each layer has its own temperature profile, its own chemistry, and its own behavior. The deepest layers contain water ice clouds. Above those sit clouds of ammonia and ammonium hydrosulfide. Higher still, a layer of methane dominates. Above the methane, the atmosphere thins out into the stratosphere. Above the stratosphere comes the thermosphere, and at the very top sits the ionosphere, where solar radiation strips electrons from molecules and creates a zone of electrically charged gas. The dark beads sit in the ionosphere, the star shape sits in the stratosphere. Between those two layers is a region called the upper stratosphere and lower thermosphere, roughly 400 kilometers of atmosphere that sits between the methane chemistry below and the ionospheric activity above. This region has never been directly sampled. Spacecraft visiting Saturn, including the Cassini mission, studied the planet from orbit and made detailed measurements of many atmospheric layers. But the upper stratosphere and lower thermosphere of Saturn occupy a zone that is too high for atmospheric probes descending into the planet and too low and dense for spacecraft orbiting above it. Getting an instrument into that 400-kilometer gap without burning it up or crushing it would require a specifically designed atmospheric entry vehicle, something no mission to Saturn has carried. The Cassini spacecraft did pass through Saturn's upper atmosphere during its final orbital dives in 2017, gathering data from the very top of the atmosphere before plunging into the planet and ending its mission. But those passes were brief, dangerous, and covered only the highest and most tenuous atmospheric layers. The 400-kilometer gap between the dark beads and the star shape remained unmeasured. What that gap contains in terms of chemistry, dynamics, and structure is genuinely unknown. Scientists can make inferences based on what they know about Saturn's other layers, models of atmospheric circulation, and comparisons to similar gas giants like Jupiter, Uranus, and Neptune. But the gap is wide enough and distinct enough that inferences from adjacent layers carry significant uncertainty. The two newly discovered structures, the dark beads and the star shape, sit on either side of this gap, like brackets around a missing chapter. Whatever process creates or sustains one or both of those structures might operate primarily within the gap, in a region that has never been directly observed. There could be atmospheric dynamics, chemical reactions, or even wave patterns in the gap that connect the two anomalies to a single underlying cause. Or the two structures might be completely unrelated, produced by different mechanisms operating independently at different altitudes, and connected only by their shared geography on the same planet. Scientists currently cannot distinguish between these possibilities because they lack data from the gap itself. The James Webb Space Telescope can detect features in the layers it can see, but it cannot see through Saturn's atmosphere into the gap. Infrared observation from space gives you the surface chemistry of each layer, not the hidden dynamics of the layers beneath. A future dedicated Saturn probe, one specifically designed to survive entry into the planet's atmosphere and transmit data from the gap layer before being crushed or destroyed, would change everything. Such a mission is being discussed in the planetary science community. It has not been funded or built. Until then, the 400-kilometer gap remains one of the most significant unexplored regions in the solar system. And the fact that both structures flanking it are completely inexplicable only strengthens the case for going back. Because Saturn, as strange as it is only one planet, and the strangeness of its atmosphere raises a question that applies to every other planet we have ever studied. Jupiter has storms the size of Earth that have raged for centuries. Neptune has winds blowing at over 1,000 miles per hour, the fastest sustained winds on any planet in the solar system. Uranus rotates on its side, tilting its poles toward the sun for decades at a time. Venus has a runaway greenhouse effect so extreme that its surface temperature melts lead. Mars has dust storms that swallow the entire planet for months. Every planet in the solar system has something dramatic going on. And yet none of them has anything like what Saturn is now showing. Jupiter is the most atmospheric planet in the solar system, studied in extraordinary detail by the Galileo probe, the Juno spacecraft, and countless Earth-based telescopes. Its banded cloud layers, its great red spot, its intricate swirling eddies, all of these have been mapped and modelled in detail. Jupiter's upper atmosphere contains lightning storms, wave patterns, and jet streams that produce spectacular visible structure. None of it includes persistent, discrete dark beads arranged in a chain at a specific latitude band. None of it includes a geometric multi-armed star shape in the stratosphere. Uranus and Neptune, the ice giants, have frigid atmospheres dominated by methane and hydrogen. Both show banded structure and some evidence of storm activity. Neither carries structures resembling Saturn's anomalies. Neptune's Great Dark Spot, observed by Voyager 2 in 1989, was a massive storm comparable in some ways to Jupiter's Great Red Spot, but it disappeared by the time the Hubble Space Telescope looked again a few years later. Temporary storms and vortices exist on ice giants. Stable, geometric, chain-like bead structures do not. Venus has one of the most extreme atmospheres in the solar system, with sulfuric acid clouds, crushing pressure, and temperatures near 900 degrees Fahrenheit at the surface. Its upper atmosphere has been studied by multiple spacecraft, including the Venus Express mission. Researchers have found wave patterns, polar vortices, and unusual cloud structures. No beads, no star shapes. Mars has an extremely thin atmosphere, only about 1% as dense as Earth's at the surface. It carries dust devils, regional dust storms, and seasonal polar ice caps. Its atmospheric dynamics are relatively simple compared to the gas giants. There is no comparison to be made with Saturn's stratospheric anomalies. Earth's own stratosphere has been studied more thoroughly than any other planetary atmosphere in history. It contains the ozone layer, jet streams, sudden stratospheric warming events, polar vortices, and wave phenomena. Researchers have looked for persistent geometric structures and found none. The closest analog on Earth might be atmospheric gravity waves, which can produce regular patterns visible in cloud formations, but those are transient and circular, not stable, multi-armed geometric shapes. The uniqueness of Saturn's anomalies creates a classification problem. In planetary science, understanding a phenomenon means finding analogs, comparing it to similar things on other worlds, and using those comparisons to identify the common physical process. If only one planet in the solar system displays a particular feature, the analogical approach breaks down. Scientists cannot triangulate the cause using comparisons, because there is nothing to compare it to. This makes Saturn's atmospheric structures among the most scientifically isolated discoveries of the modern era. They are real, confirmed, measured, and strange in a way that no existing framework can account for. And the strangeness does not stop at observations. Because several competing theories now exist for what might explain these discoveries, and each theory, if correct, demands a fundamental rethinking of physics at a completely different scale. Dark matter has never been directly detected. For decades, that fact sat quietly in the background of cosmology. Scientists were confident that dark matter existed because of its gravitational effects. Galaxies rotate in ways that make no sense without it. Clusters of galaxies bend light far more than their visible mass should allow. The structure of the cosmic web matches simulations that include dark matter and fails to match those that leave it out. But the particle itself, whatever dark matter actually is, has stubbornly refused to appear in any detector built to find it. Billions of dollars have been spent on underground laboratories, shielded from cosmic rays, looking for the faint recoil that would result from a dark matter particle colliding with an ordinary atom. Nothing. That absence encouraged a small but persistent community of physicists to ask a different question. What if dark matter does not exist? What if gravity itself works differently than Newton and Einstein described, in a way that produces the observed galaxy rotation curves without requiring any invisible mass? The most developed version of this idea is called modified Newtonian dynamics, or by its initials MOND. It was first proposed in the 1980s by physicist Mordechai Milgrom. The core idea is simple. Newton's second law says that force equals mass times acceleration. At high accelerations, this works perfectly, confirmed by centuries of experiment. But Milgrom proposed that at very low accelerations, the kind experienced by stars at the outer edges of galaxies, gravity behaves differently. It falls off more slowly than Newton's formula predicts. If gravity is stronger at these low accelerations than the standard formula says, then galaxies can hold themselves together at their outer edges without needing any additional invisible mass. The stars orbiting far from the galactic center experience this modified gravity, which provides the extra pull that dark matter was invented to supply. The idea had early successes. MOND predicted the rotation curves of many individual galaxies remarkably well, often better than dark matter models that needed to be fine-tuned for each galaxy. It also correctly predicted a relationship between the visible mass of a galaxy and its rotation speed, called the Tully-Fisher relation, which dark matter models struggled to reproduce without careful adjustment. But MOND ran into serious problems at larger scales. Galaxy clusters, which require enormous amounts of dark matter in the standard model to explain their gravitational behavior, are very difficult to explain under MOND. The cosmic microwave background, the afterglow radiation from the Big Bang, has a pattern of temperature fluctuations that the standard dark matter model explains well and MOND struggles with. And the collision of galaxy clusters, particularly the bullet cluster, where the visible gas and the gravitational mass appear to be in different locations, is extremely hard to reconcile with any theory that removes dark matter entirely. The James Webb Space Telescope has added new pressure to the debate. The early, massive galaxies and the cosmic vine both require either extremely rapid dark matter assembly or some alternative mechanism for building structure quickly. MOND alone does not automatically provide that mechanism, since it changes the behavior of gravity without changing the total amount of mass available to build structures. Some theorists are now working on hybrid models, theories that modify gravity at large scales while keeping dark matter at small scales, trying to capture the strengths of both approaches. The debate is unresolved, and it is part of a broader upheaval in theoretical physics that the telescope's discoveries have accelerated. Because modifying gravity is only one path forward. Another path goes somewhere even stranger. Gravity is the oldest force in physics. Newton described it in the 17th century. Einstein refined it in the 20th century, revealing that gravity is not a force in the traditional sense at all, but a curvature of space-time caused by mass and energy. Objects in freefall follow the straightest possible paths through curved space, which is why planets orbit stars and why light bends near massive objects. Einstein's theory of gravity, called general relativity, has passed every test that scientists have thrown at it. The precision of GPS satellites depends on relativistic corrections to gravity's effect on time. Gravitational waves from colliding black holes match the theory's predictions to extraordinary accuracy. The perihelion precession of Mercury's orbit, a small deviation that Newton's formula could not explain, falls exactly within Einstein's calculations. General relativity is one of the most tested and most successful theories in all of science, and it may be incomplete. The Hubble tension, the uneven expansion of the universe, the formation of massive structures earlier than any model permits, and the failure of cold dark matter to match what the telescope sees in the early universe all point toward the same possibility. That general relativity, as precise as it is at the scales we can test it, breaks down or changes behavior at the extreme scales of cosmology. On the scale of atoms and particles, quantum mechanics rules. On the scale of planets and stars and laboratory experiments, general relativity and Newton's gravity work with stunning precision. But the scale of galaxy clusters, cosmic filaments, and the observable universe as a whole has never been a domain where gravity has been independently tested without the support of a model built around dark matter. Scientists assumed that the same equations that work at smaller scales simply extend upward to all scales. That is a reasonable assumption, but it is an assumption. And the telescope is providing the first data good enough to seriously stress test it. Some researchers are working on extensions to general relativity that change its behavior at the very low accelerations found in the outskirts of galaxies and in the dynamics of the cosmic web. These theories, sometimes grouped under the label modified gravity, predict slightly different growth rates for cosmic structures and slightly different distributions of mass across the universe than standard general relativity with cold dark matter. The early data from the telescope is a better fit for some of these modified gravity predictions than for the standard model. Structures form earlier, grow larger, and arrange into more elongated shapes under certain modified gravity scenarios, matching what the telescope actually sees. This does not mean general relativity is wrong at any scale currently tested. Every solar system observation, every gravitational wave detection, every black hole image remains fully consistent with Einstein's equations. The possible breakdown would be at scales far beyond anything tested in laboratories or within our own solar neighborhood. But testing gravity at cosmic scales requires exactly the kind of data the telescope is now delivering. And several theorists believe that within the next decade, the telescope's catalogue of early galaxy shapes, sizes, and distributions will be precise enough to distinguish between standard general relativity with dark matter and modified gravity models with no dark matter. The answer will reshape physics. Either path leads somewhere new. And to understand how we got here, how a single telescope changed the entire conversation about the laws of nature, it helps to understand what the James Webb Space Telescope actually does when it looks at the universe. Not just what it finds, but how it manages to see things that every previous instrument in human history missed entirely. Light has a speed limit, 300,000 kilometers per second, roughly 186,000 miles per second. Nothing in the universe moves faster. And because light travels at a finite speed, every time you look at something far away, you are seeing it as it was in the past, not as it is now. When you look at the moon, you are seeing it as it was about 1.3 seconds ago. When you look at the sun, you are seeing it as it was 8 minutes ago. When you look at the nearest star beyond our sun, Proxima Centauri, you are seeing it as it was 4 years ago. And when you look at a galaxy 2 billion light years away, you are seeing it as it existed 2 billion years in the past. The telescope is a time machine, and the further it sees, the deeper into history it reaches. Previous space telescopes, including the Hubble Space Telescope, could see extraordinarily far. The Hubble Ultra Deep Field image, a long exposure pointed at a tiny patch of sky, captured galaxies over 13 billion light years away. That was already remarkable. But seeing those distant galaxies in detail, determining their masses, shapes, chemical compositions, and ages, required more than just distance. It required resolution, light collecting power, and sensitivity to the right wavelengths. Here is where the James Webb Space Telescope changes everything. First, its mirror is enormous. The primary mirror spans 21 feet across, made of 18 hexagonal segments coated in gold to maximize infrared reflectivity. The Hubble mirror was only 8 feet across. More mirror area means more light collected, which means fainter and more distant objects become visible. Second, and most critically, it sees in infrared. This matters because of a phenomenon called redshift. As the universe expands, the space between galaxies stretches. Light traveling through expanding space gets stretched along with it. A photon that started its journey as visible blue light billions of years ago arrives at Earth as infrared light, stretched well beyond what human eyes or visible light telescopes can detect. Hubble was designed primarily for visible and ultraviolet light. The most ancient galaxies in the universe, the ones from the first few 100 million years after the Big Bang, emit their light in the visible spectrum but arrive at Earth deeply redshifted into the infrared. Hubble could barely see them. James Webb was designed specifically to catch them. Third, it operates in space, far from Earth's atmosphere, which absorbs most infrared wavelengths and would make ground-based infrared observation nearly impossible at these sensitivities. But James Webb also orbits nearly 1 million miles from Earth at a gravitationally stable point called the second Lagrange point, where it stays in Earth's shadow. This keeps the telescope cold, which is critical for infrared observation, because infrared telescopes need to be colder than the light they are trying to detect. The combination of these factors gives the telescope a window into the universe's earliest moments that no previous instrument possessed. The galaxies, structures, and anomalies it is finding were always there, waiting in the dark. For decades, humanity simply lacked the instruments sensitive enough to see them. And what the telescope reveals when it looks into that deep infrared darkness is that seeing further back in time is not just seeing older things. It is seeing a universe that played by different rules than the one we live in today. The universe has changed. That sounds obvious. Of course, the universe has changed over 13 billion years. Stars formed and died, galaxies merged and grew. The cosmic web took shape. Everyone knows the universe looks different today than it did in its youth. But the changes revealed by the telescope go deeper than anyone expected. The early universe does not just look different from today's universe the way a teenager looks different from an adult. It operates differently. The processes driving galaxy formation, the rates at which structures grow, and possibly the behavior of the fundamental forces themselves appear to have shifted in ways that the standard model did not predict. In the early universe, star formation was more efficient. Galaxies were building stars at rates tens or hundreds of times higher than any galaxy achieves today. The Milky Way currently forms a few new stars per year. Early massive galaxies were forming hundreds of new stars per year, sometimes for billions of years continuously. That efficiency has never been fully explained by models of gas cooling and collapse, which predict lower star formation rates under early universe conditions. Dark matter appears to have behaved differently in the early universe too, or at minimum, its effects on structure look different than models predict. The shapes of early galaxies, more elongated and filamentary than expected, suggest that whatever was organizing matter into structures was doing it in a way more consistent with wave-like dark matter behavior than with the classical cold dark matter that dominates the predictions. The expansion of the universe also appears to have varied over time. The rate of expansion was different during the era when the cosmic vine formed than it is today, and the Hubble tension suggests that even our measurement of that rate is inconsistent depending on when and where we look. The behavior of dark energy, the force driving the current expansion, may have been different in the early universe than it is now. All of this points toward a universe where the dominant forces and their relative strengths were not identical throughout all of history. Physicists call this the evolution of fundamental constants, and it is one of the most controversial ideas in modern science. If the strength of gravity, or the speed of expansion, or the behavior of dark energy has changed over cosmic time, then every equation that assumes these values are fixed needs to be revisited. The telescope cannot directly measure whether fundamental constants have changed, but it can measure the structures that those constants produced at different points in cosmic history. And the structures it finds in the early universe are consistently more extreme, more organized, and more massive than any set of fixed constants in the Standard Model predicts. This is the deepest implication of the telescope's discoveries, deeper than any single anomaly, deeper than the cosmic vine or the little red dots or Saturn's impossible shapes. The universe may not be governed by the same physics at all times. The rules may have evolved, and if they have, every model built on the assumption of fixed constants is, at minimum, incomplete. Scientists are only beginning to build the mathematical tools needed to test this possibility. The data from the telescope will be the proving ground. But before any new theory can be built, the old puzzle pieces have to be fully understood. And one of the most precise and revealing tools for understanding the little red dots was a technique that turns light itself into a fingerprint. Every element in the universe has a signature. When atoms absorb or emit light, they do it at very specific wavelengths. Hydrogen absorbs light at certain precise colors, oxygen at different ones, carbon at others. These signatures are fixed by the laws of quantum mechanics, which govern how electrons jump between energy levels inside atoms. Those jumps produce or absorb photons of exact wavelengths, and because the laws of quantum mechanics are the same everywhere in the universe, the signatures are universal. Astronomers split the light from distant objects into its component wavelengths using an instrument called a spectrograph. The result is a spectrum, a rainbow-like spread of light intensity across wavelengths. In that spectrum, certain wavelengths appear as dark lines where light has been absorbed, and others appear as bright lines where light has been emitted. The pattern of those lines is the fingerprint of whatever gas or material lies between the source of light and the telescope. Reading that fingerprint tells you what an object is made of. It also tells you how fast the object is moving, because motion stretches or compresses the wavelengths of light through the Doppler effect. And for objects billions of light years away, the stretching caused by the universe's expansion, the redshift, tells you exactly how far away the object is, and therefore how far back in time you are looking. When researchers first spotted the little red dots in the telescope images, they could not determine what they were from the images alone. They looked like compact, reddish smudges. Without spectral data, they could have been almost anything. Running spectroscopy on objects 11 billion light-years away is a technically demanding process. The light arriving from those objects is extremely faint, and extracting a usable spectrum requires long exposure times and extremely sensitive detectors. The James Webb Space Telescope's near-infrared spectrograph can observe up to 100 objects simultaneously, and the team running the Little Red Dot investigation used this capability to collect spectra from dozens of them at once. The spectra came back with something surprising. The emission line patterns from many of the little red dots matched the signatures of hydrogen gas being ionized by an extremely energetic source, consistent with the behavior seen around actively feeding black holes. But the overall shape of the light spectrum, the way brightness varied across wavelengths, did not match known quasar patterns. Quasars are bright across many wavelengths. These objects were bright only in narrow infrared windows. The interpretation that emerged from the spectral data was that the energetic source inside each little red dot was being viewed through a dense surrounding envelope of gas. The envelope absorbed most of the emitted light, letting only certain wavelengths through. The wavelengths that escaped matched what you would expect if the envelope was made primarily of hydrogen gas at high temperature. This was the key evidence for the black hole star interpretation. The spectral fingerprint matched a supermassive black hole wrapped in a sphere of extremely hot hydrogen, exactly as the theory predicted. The gas cocoon was doing what cocoons do, blocking most of the light and letting only specific signatures escape. The fact that so many of the little red dots share similar spectral fingerprints suggests they are the same type of object, a new category of cosmic structure appearing consistently in the early universe. Cataloguing all of them, measuring their masses and distances, and determining whether they are truly black hole stars or something else is ongoing work that will take years. But the tool that cracked them open was light itself. The same light that left those objects 11 billion years ago, carrying the fingerprints of their chemistry, arriving at a gold-plated mirror 1 million miles from Earth, and telling a story that no model had predicted. Stars age slowly. A star like our Sun will burn steadily for about 10 billion years before exhausting its hydrogen fuel and swelling into a red giant. More massive stars burn hotter and die faster, sometimes in just a few million years. But even the most massive, shortest-lived stars take millions of years to run their full course. And galaxies which contain billions of stars cycling through birth, life and death across enormously long timescales are supposed to age on a scale that dwarfs individual stellar lifetimes. A fully quenched galaxy is one where all of that cycling has essentially stopped. The raw material for new star formation, giant clouds of cold hydrogen gas, has been exhausted or expelled. The remaining population of stars is aging toward red dwarfs and stellar remnants. The galaxy is not dead in the sense of being dark, but it is no longer growing, no longer creating anything new. Winding down. In today's universe, quenched galaxies are common. They tend to be the large, elliptical galaxies found at the centers of galaxy clusters, massive systems that used up their gas supply long ago and have been coasting ever since. They look reddish because they are populated by old, cool stars rather than hot young blue ones. The expectation in the standard model was that galaxy quenching follows a predictable timeline. A galaxy forms, builds up its stellar population over several billion years, and then, under the influence of supermassive black hole feedback or the stripping of gas by a surrounding hot medium, gradually slows its star formation and eventually stops. The process should take multiple billions of years in total. Inside the cosmic vine, the two largest galaxies are fully quenched, and they exist at a time when the universe was only about 2 billion years old. The math is crushing. For a galaxy to be fully quenched at 2 billion years, it must have formed, built a stellar population large enough to be counted among the most massive galaxies of its era, used up or expelled all of its gas, and stopped forming stars, all within roughly 2 billion years of the Big Bang. For context, the Milky Way, which is still actively forming stars today, has been doing so for over 12 billion years and still has gas left. What could drive quenching this fast? The most compelling mechanism is extreme quasar activity. If the supermassive black hole at the center of one of these galaxies went through a phase of feeding at the maximum possible rate, the energy it released could have heated and expelled the galaxy's entire gas supply in a geologically short time. Some models suggest this can happen in as little as a few 100 million years under extreme conditions. But for this to explain the vine's quenched galaxies, the black holes driving the quenching would need to be extraordinarily massive themselves, capable of generating the enormous energy output needed to strip a galaxy of its entire gas reservoir. And extraordinarily massive black holes in the early universe bring the discussion directly back to the little red dots and the black hole star mechanism, where extreme early feeding creates enormous black holes fast. Everything connects. The quenched galaxies point to extreme black holes. The extreme black holes might be the remnants of black hole stars. The black hole stars are the little red dots. And the little red dots are scattered throughout the early universe in numbers that suggest this was not a rare event, but a dominant phase of cosmic evolution. If all of these threads are correct, the first 2 billion years of the universe's history were far more violent, far more rapid, and far more structured than anyone imagined. And what that means for humanity's place in the story of the cosmos is something worth sitting with. Physics is not abstract. Every piece of technology in your life rests on physics. Your phone communicates using electromagnetic wave equations written in the 19th century. The microchips inside it operate on quantum mechanics developed in the 20th century. The GPS signal telling you which turn to make relies on corrections calculated using Einstein's general relativity. Take away the physics, and none of it works. This is why the discoveries from the James Webb Space Telescope are not just interesting for astronomers. If the standard model of cosmology requires a fundamental rewrite, the ripple effects spread into physics at every scale. Start with dark matter. If the telescope's discoveries force physicists to abandon cold dark matter in favor of fuzzy dark matter, or to abandon dark matter entirely in favor of modified gravity, the mathematical tools used to model everything from the formation of planets to the behavior of black holes get revised. Those tools underpin simulations used in materials science, nuclear physics, and even the design of future spacecraft and communication systems. Shift to gravity. If general relativity breaks down at cosmic scales in ways that require modification, the question immediately becomes whether any of those modifications affect the behavior of gravity at smaller scales, possibly in ways too tiny to detect in current experiments, but significant enough to affect precision instruments over long baselines. Space navigation, deep space communication, and the management of satellite constellations all depend on gravitational models precise enough to predict orbital decay and trajectory deviation over years. Move to dark energy. If the expansion of the universe is clumped and variable rather than smooth and constant, and if that variability reflects a true property of dark energy rather than a measurement artifact, then the long-range predictions of cosmological models shift. Scientists use those models to calculate the timescale over which the universe will continue to expand, when galaxy formation will end, and how long the conditions for life are likely to persist in any form. A revised dark energy changes every one of those projections. None of this means that your phone will stop working next year. The tested, verified parts of physics remain solid. General relativity works perfectly at every scale it has been tested. Quantum mechanics powers every transistor on Earth without any sign of breakdown. The specific equations used to design today's technology are not in question. What is in question is the larger framework that connects all of these verified equations into a complete picture of reality. The standard model of cosmology is that framework at the largest scales, and the telescope is revealing cracks in it that cannot be patched with small corrections. Building a new framework takes time. It took decades for Einstein's general relativity to fully replace Newtonian gravity after the 1905 predictions were made. It took decades more for the quantum mechanical revolution to produce the transistor. The theoretical work done today in response to James Webb's discoveries may not produce technological consequences for generations. But the work is being done, and the scientists driving it know that what they are building now, the new equations, the new models, the new understanding of dark matter and gravity and expansion, will eventually flow downward into technology in ways that are impossible to fully predict from the inside of the revolution. And the people leading that revolution are not working from a position of certainty. They are working from a position of genuine, productive, sometimes uncomfortable disagreement. The debate about what the telescope's discoveries actually mean is one of the most intense in modern science. Physics has always been comfortable with debate. Einstein argued with Bohr for decades over the interpretation of quantum mechanics. The debate over the nature of black holes lasted most of the 20th century. Arguments about the value of the Hubble constant persisted for decades before instruments became precise enough to make the disagreement itself a scientific problem rather than a measurement error. The debates triggered by the James Webb Space Telescope are operating at that same level of intensity and consequence. And the scientific community is not unified on what the discoveries actually mean. One camp, broadly described as conservative, argues that the standard model needs refinement, not replacement. These physicists point out that the telescope is young, its calibrations are still being optimized, and some of the most dramatic claims about impossibly massive early galaxies have already been revised downward, as better spectroscopic data replaced early photometric estimates. The 6 galaxies that broke the internet in February 2023 were initially estimated to be far more massive than follow-up spectroscopy confirmed. They are still unusually massive, they are still challenging. But the initial panic overstated the crisis. This camp argues that the standard model is resilient. Cold dark matter with modifications at small scales, combined with refinements to early universe star formation efficiency, may be capable of producing the structures the telescope sees. The Hubble tension might resolve with better understanding of systematic errors in distance measurements. The quenched galaxies and the cosmic vine might fall within the tail end of statistical predictions rather than requiring new physics. The other camp, broadly described as reformist, argues that the accumulation of anomalies is too consistent to explain away with calibration improvements and statistical outliers. They point out that the telescope was expected to cause a few surprises and confirm the overall model. Instead, it has produced surprise after surprise in the same direction. Structures too large, too organized, and too early. That consistency, they argue, is signal rather than noise. The reformist camp is subdivided further. Some push for fuzzy dark matter, some push for modified gravity. Some argue that the early universe conditions were so different from today that star formation and galaxy assembly operated by mechanisms that have no direct analog in the modern universe, requiring entirely new astrophysical models for that era. Some take the most radical position, suggesting that the cosmological principle itself needs to be abandoned and that the universe has genuine large-scale asymmetries that change the foundations of the entire field. Saturn's atmospheric anomalies add a separate dimension to the debate. Planetary scientists find themselves in a different kind of disagreement, because their models deal with atmospheric dynamics rather than cosmological structure formation. But the pattern is the same. Known mechanisms do not produce what the telescope found. The community is split between those who believe an unknown variant of known atmospheric physics is responsible, and those who believe the beads and the star shape require a completely new category of atmospheric phenomenon. Both debates will be settled by data. More telescope time on the early universe, more detailed spectroscopy of the little red dots. A future Saturn atmospheric probe. The resolution will not come from theory alone. It will come from measurement, from comparing predictions against reality until one framework fits and the others are set aside. That process is underway. It is slow by the standards of public attention and fast by the standards of science. And it is happening against the backdrop of a question so large that it rarely appears directly in scientific papers, but sits behind every one of them. Every great telescope in history has done the same thing. It has moved the boundary of what is visible, and every time that boundary moves, the universe turns out to be stranger, larger, and more complex than it appeared from inside the previous boundary. Galileo's telescope revealed that Jupiter had moons, that the moon had mountains, and that the sun had spots, all of which contradicted the prevailing model of perfect, unchanging celestial spheres. The universe was suddenly messier and more dynamic than anyone had assumed. The discovery of galaxies in the 1920s revealed that the universe was far larger than a single galaxy. The observation of the cosmic microwave background in the 1960s confirmed the Big Bang and showed that the universe had a beginning. The Hubble Space Telescope's deep field images revealed a universe containing hundreds of billions of galaxies, far more than anyone expected. At each step, the universe expanded in both size and strangeness, and at each step, scientists discovered that the model they had built to describe the previous boundary was incomplete. The James Webb Space Telescope is the latest version of this pattern, and the strangeness it has revealed, the cosmic vine, the impossibly massive early galaxies, the little red dots, the quenched galaxies, Saturn's dark beads, the stratospheric star, the Hubble tension, the signs of uneven expansion, is consistent with a universe that has always been this complex. A universe in which the rules were richer, the processes faster, and the structures more organized than any model built from within our limited window of observation could have predicted. The question the telescope leaves open is whether this strangeness represents holes in our current understanding that new data will fill, or whether it represents something more fundamental. A signal that the universe operates by principles we have not yet discovered, principles that a more complete physics would describe naturally. History suggests the second option is at least partially true. Every expansion of the visible boundary has required new physics to describe what appeared there. Quantum mechanics was needed to explain the behavior of atoms, relativity was needed to explain the behavior of light and gravity at high speeds and in strong fields. The cosmic microwave background required the Big Bang and inflation. Dark matter and dark energy were proposed to fill gaps that visible matter left open. The James Webb Space Telescope is filling in a new part of the picture, the earliest accessible moments of cosmic history, and finding that the gaps left by current physics are significant. The structures in that early era do not fit neatly into any box. They require either a heavily modified version of the model we have, or a genuinely new framework. That framework is being built right now, in universities, in observatories, in simulation labs, and in the pages of preprints published every day. The scientists writing those papers are working with incomplete data, competing ideas, and the normal productive friction of a field in the middle of a revolution. The telescope continues to observe. Every new pointing adds data. Every new spectrum refines an estimate or overturns an assumption. The picture will sharpen over the coming decade in ways that cannot be fully predicted from where we stand now. What can be said with certainty is this: the universe hid its strangest features from us until we built an instrument sensitive enough, cold enough, and wide enough to catch the light that carries their fingerprints across 11 billion years of expanding space. We built that instrument. It is working. And what it is telling us, chapter by chapter, discovery by discovery, is that the cosmos is more alive, more structured, and more inexplicable than any model human minds have yet produced. The question now is whether our minds are ready to build the model that finally fits.